So for those of you who don't know, like for the last 2 years, I've pretty much taken a break. And I spoke at every con for like a day, like everybody saw me everywhere forever. And I rotated, I only ever did speeches 2 times in a row. That's the most I've ever done. This is a speech I heard yesterday from Trevor. We need a new speech. So I was in DC on Monday. I just gave a speech at the Cyber Crime Security Nexus, which is the first version of this new conference where they're trying to, everybody, this is going to be all you're going to hear from now on out, because I've already heard this from 100 different colleges and everything. It's all going to be cyber, 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 cyber. The word that we tried to get rid of a decade ago, we're back. And this is all we're going to do is talk about cyber everything. So cybersecurity, cyber forensics, cyber everything. Cyber sex, yes, with robots. There is a con for robot sex.
They just canceled it.
They just canceled it. That is correct. So,
I guess no one came.
In case that didn't get picked up on the mic, because no one came. Right. That was pretty funny. All right. So you can go in the comment section for the. Anyway, this is kind of a revisit of a speech. I did a speech 2 years ago at ShmooCon, and it was about forensics imagers. And so this is a refresh of what's happened in the last 2 years with forensics imagers. And I, personally, for those of you who don't know who I am, so just ignore anything that says CSX on it. That was what I did Monday. So I didn't have enough time to put Skydog Con. Yeah. So in this particular instance, I do forensic. I actually do criminal forensics. And it's all digital stuff, so cell phones, computers, equipment. I deal with a lot of criminal cases, some what you see in the news. Sometimes I'm in the news. Things like that happen. And I also have a data recovery company. I have a corporation that we actually receive drives in. We do repairs. We fix them. We recover people's data, and then we send it back out to you. So we do them kind of side by side. So the forensic side is all the paperwork and all the other stuff that happens. And then in 2007, 2008, I wrote a class on how to do forensic data recovery. So in other words, pulling heads out of drives, reassembling the drives, repairing them, doing forensics images from those, and getting back the data that the police officers can't get back, or that a lot of entities, FBI, CIA, anyway. I teach this class all over the world, and I've taught to just about every agency all over the world. So my problem is this. Forensics imagers literally suck. Forensics imagers as a whole, there has been almost no, absolutely zero improvement in the forensics imagers in the last 30 years. Every time that something comes out, and that's the premise for this talk, everything that comes out uses the same kernel, the same DD engine to basically copy everything from the drive. Now, data recovery, which if you're thinking of forensics, in my mind, when I started doing forensics and then started a data recovery company, now it's been 16 years, I thought that data recovery was going to kind of be like, well, you go to a chiropractor and they also give massages. So the massage would just be, you know, the extra stuff, and it's kind of the fluff that kind of goes with that so that you could keep making more money or do something else. Data recovery is far more extensive than forensics is. Data recovery and the data recovery community know far more about hard drives than any forensics guy you'll ever meet on planet Earth, besides maybe me. But there's a lot of data recovery guys out there that know even far more about drives than I could possibly tell you after spending every minute of my life doing this the last 16 years. So they're really far more advanced than almost all the forensics guys. The only difference is they don't handle the paperwork, they don't handle the cases, they don't do the legal side, so they don't know what they're doing with that kind of stuff. And techs really are scared by that. They really don't communicate. They have no ability to really speak and handle something like testifying in court, which I do all the time, but at least from this standpoint, none of the forensics people that are doing this have any of the knowledge that the data recovery people do or the tools. So I'm going to demonstrate this to you, and I'm going to kind of show you what we're dealing with as a whole from this standpoint. So right here, the first problem I have is that forensics people are gathering evidence from hard drives and then using that in court cases, and they're missing stuff. They're damaged drives, they're missing sectors, there's all kinds of problems, and they're using these and many times to decide, or the judge is deciding, whether or not you're going to go to jail for the rest of your life, or your physical life is at stake. Whereas data recovery people have some of the very powerful, extensive tools that can get every single sector back that the guy who's doing forensics missed for your porn, so they can get your porn collection back. That's literally like 90% of data recovery jobs are, I would like my QuickBooks database, but I really like my porn also. So that's a normal thing, and I can, I get paid to look at porn. That's really ultimately what we're talking about at this point. So thank you guys. So anyway, so as we're moving on here, so when you're doing forensics, a lot of forensics tools out there, they're really doing things for speed. There are software, and I'm not primarily talking about software because I will, but as a whole, anybody use Encase? Anybody out there doing forensics? Yes, Encase. FTK? Yeah. Other types of copiers like Disc Jockey and things like that. You guys, anybody use any of those kind of things? There's some low-end ones now that you can buy at the store where you just push a button on the little black box and it copies your hard drive from one to another. Anybody dealing with any of those? I'm sure that somebody here is also doing corporate stuff where you have to clone them and use something like Ghost and then distribute them back out through the networks. Those kind of things? Yes? Okay. So the problem with most of those is speed. Most of those tools, the software tools, a lot of things, they're fairly slow. They're usually limited to the speed that you're able to plug stuff in the hopes that your write blocker and the content that you're trying to protect along the way does a good job. So a lot of forensics guys will go out there and buy third-party tools. Now, this particular one right here, this one, there's several, they're called TD1, 2, and 3. There's 3 versions. Those are made by Guidance. The Guidance makes Encase. And they bought Tableau. So Tableau is the company that they now own, and that's a Tableau. And again, there's 3 different versions: TD1, TD2, and TD3. And they're high-speed forensics imagers. And when I say high-speed, you're normally, without hardly any effort, plugging these drives in, and you're imaging them 200 to 300 gigs an hour, basically. The majority of them are going to reach that. And the beauty of these, most of the time, is that they're very easy to use, because when you're walking into a facility, like a police are there, or there's lawyers there, everybody's talking to you. It's like any other consulting gig that you ever do, except they never leave you alone. So you're there at the table all the time talking to these people, but still have to accomplish your job at the same time. So these tools make it extremely easy for you to not do a dumb thing. Literally, you can plug in one side of the drive to your source and one side of the drive, this device, into your drive for your destination, hit a button and go. That's literally what you can do. So, but they have a lot of advantages. Speed is really the primary one, and getting rid of the dummy cycle. And then they also do verification and spit things out in files and take care of everything for you. This is pretty much the breadth of the majority of them that are out there. There's a lot more, but as a whole, they really make no difference, and I'll try to explain those in a second. But this one down here, and I've got all of these, and I've tried all these, and I've also got a whole lot more than what we have here on the screen. This one right here is one that I commonly use. It's called a Falcon, and you'll see this little interface. It's a really cute interface because it looks exactly like Star Trek. So it's really nice when you go to add stuff. It looks exactly, it has the swoop and the whole thing. It looks exactly like Star Trek. So I really commend them on making it look really, it's the only Star Trek interface I have on all the devices that's useful. So that's kind of cool, actually. And very efficient. I was more surprised that you could actually use a Star Trek interface and it be efficient. So, all right, so we're going to talk about all of these things. Now, most of these tools, if there is a problem, if there's an error on the hard drive, this is the biggest thing, is that if there is a single sector in a lot of cases that fails, sometimes the tool will just completely fail. Sometimes, if it can figure out how to continue, it'll just pad that sector with zeros or mark something with zeros. But most of the time, the tool fails. It doesn't copy the drive at all. It just stops. If you get enough errors, literally none of the tools will make it through any of them, nor will software most of the time. And my problem, again, is that there's a lot of things that you can do that they don't do anything. And I'm just giving you like a quick little list down here on the bottom, which is reverse imaging, ignore ECC, multipath. You don't have to know what any of this stuff means yet. You will by the end of the talk. But the whole problem is that forensics has not improved as far as their imaging process ever in 30 years. They're doing the same stuff they've always done, although these other things are available. So then you ask the question, why aren't they adding these things into their tools? They have hardware, they have equipment. They could add all these advanced features into their tools. And primarily it's money, but one of the other things is rather than spend the money or the time on doing things, they don't even want you to know that these other things are capable. And I have actual proof of this, that they're actually, the companies who make these tools are doing things to try to stop other people from even finding out about the data recovery tools, these advanced features, and all these other things that they could do. Because why would you ever buy their tools at all if these other tools did everything? So I have a specific instance where I heard a story directly from one of the guys who runs one of the companies. It's called Atola. Atola is a company, it's a data recovery company that makes a new forensics imager. And they were going to an Encase conference. Encase runs a big conference every year for forensics people, and it's called CEIC. It's not anymore, but it was as of last year. And they had a table, just like every other vendor that you would walk by their table and you would go see their stuff. Well, I did a talk at ShmooCon about how their stuff was trumping everything that the imagers would do at Tableau, at Guidance, and everything else. So after I did this talk, I actually got a phone call from Guidance and Tableau. They spoke to me on the phone and started talking to me about all these things that they wanted to add to their imagers and all these things that they needed to improve. And I'm like, all right, awesome, I accomplished the task. I think that they're actually going to make some changes, and as forensics people, we might get better tools. And then about 2 days later, I got a call from Dimitri at Atola, and he goes, I don't know what you did, but it worked. My table's $50,000 now. So it went from $5,000 to $50,000, and he was told directly that they didn't want him showing up at any of the conferences because they didn't want anybody to see competing products that do the things that his product does. They just wanted them to buy their stupid, dumb piece of crap. And I have a huge problem with companies that are doing stuff to stop technology just because they don't want to pursue money or spend money to try to actually do something from a standpoint of to improve the product. So let's get on to these kind of things. So I've testified a number of times. I've testified in federal court, state court, a number of smaller courts. And this is a common thing I see even from agents and stuff that are sitting on the stand. They'll be asked, were you able to copy every sector on the drive? And they will say, yes, I have 100% of the drive copied. Now, here's the problem I have is that they don't really understand anything about the drive. And what they actually are saying is they don't know what they didn't get, because there's a huge amount of data that's written to the drive that they don't have access to that actually might include user area, that might actually include users' data. And so they don't even know the answer to the question. But the bigger problem down here is the one where if they had a problem or there was an error and they did know about it, then it was okay that it was padded with zeros. Data recovery people don't pad it with zeros. They have to do everything they can to avoid it. They try to read every single sector, and even if a sector is damaged, they can read half of it or more. They will actually keep that content rather than just throw it away. So they didn't copy every sector. They didn't even have a chance to. There's a couple other things out there that try to explain things, but even if there's nothing else, I get a point across on this talk is that one thing is I will teach you some stuff about hard drives. One of the things about hard drives is this: SMART, which is self-monitoring analysis and reporting technology. It is a tool that's basically running on your drive. Many of you have heard of it because you run a little tool to make sure that your drive's healthy, and it'll just say okay or nothing. They're pretty extensive tests. There's a lot of things that can actually happen in SMART. But one of the things that people who are doing forensics images rely upon is something called a hash. At the end of copying a hard drive, they hash it so they can say, well, this algorithm says that I have a good copy of the drive, then they verify it. During the process of imaging a drive, the data can actually change. So from the beginning of starting the imaging process to the end of the imaging process, if the drive detects that there's some error or there's some reason why it can't read a sector, it can actually mark that as bad and substitute it on the fly. And the result that they're actually getting in the image won't include the actual original content that was there in the beginning. Now, it's rare. It doesn't happen every day, and it's not supposed to happen the majority of the time, but it can happen. And SMART is one of these items that tracks it. So if you pulled a table at the beginning and you said, hey, SMART, let me read all what your sectors say they are right now, then you image your drive, and at the end, if that number changed, then it would reflect that there was something that was wrong. So this, again, is one of those things where forensics people are basically saying, I have a hash, here's my result, and this makes me good, which is it comes after the fact, not before the fact. When you hash something, you've already got a copy of it, so you don't know that it changed before you got a copy of it. So you're only getting a hash on the result. You're not getting a hash on the origination. Does that make sense to everybody? Everybody clear with this? Good. All right, so here's one of the things that happens. There's something called bad block redirection. So and this is a normal thing that happens on a drive. It happens, it's invisible to you. Your drive always tries to present itself as if it's perfect. It does not want you to know that it has errors and it has problems. No drive, even when you receive them brand new out of the box, is perfect. They all have errors. They all have physical problems. They all have sectors that have been reallocated, whether or not they were done at manufacturing time or whether or not they're done at use. So in this particular instance, what we have is something called bad block redirection. These would normally be your LBA blocks. You would have 25, 26, 27, and then you would have something that redirects, if a sector is bad, to something in something called a system table. So there is a system area of the drive that has allocated space so that you can reallocate something if something's bad, because you must always have the same number of sectors. You cannot run out of the number of sectors that you have and just diminish the size. So your partition should always remain the same size. Thank you, sir. Oh, that's nice. So ultimately, any of these things that happen, there is no way for them to know if they happened after the fact. Now, I know this will be a little bit hard to see, and I might be able to zoom in a little bit. This is a smart table, the data that's pulled from a smart table, and there are at least numbers that will tell you things. Now, there's not much of a standard. There's some problems with the standard as a whole, but they do try to track reallocated sectors. They try to track whatever else has gone wrong and whether or not there's still a problem. And if you read the table at the beginning, you can still read it at the end. Now, one of the other things, in case nobody knows this about solid-state drives don't have all of the same identifiers that hard drives have. Like, they don't have heads, so they don't need to keep track of certain things for moving ahead or doing some other things. So solid-state drives steal the same locations for other data. So if you get a data sheet from your solid-state drive, because if you pull smart information from a solid-state drive, it won't make sense. What they're actually telling you for those locations is just some bogus piece of text that they filled in, and they're not telling you the real answer. You can actually go get your data sheet for your solid-state drive and look at the table and then pull the table, and you can find out what those settings actually are and what they really mean. Because all the stuff for smart normally is for hard drives, not for solid-state drives. So you're just getting lied to when you're looking at your solid-state drives right off the bat. But just know, go pull your data sheet and look at it from that standpoint for your particular drive, and it'll tell you. Now, when forensics people are imaging their drives, this would be a report that they would get at the end of their imaging process. And you'll notice there will just be errors where it cannot read something, and they'll just note them, but they're filled with zeros. There's data that is missing on the drive. It could be a huge chunk, it could be a small chunk, or it could be not successful at all and fail. So 15, 16 years ago when I started doing this, it was pretty rare for forensics to see damaged hard drives. So it's changed a lot over the years. Over the last few years, I'm going to tell you about 25% of the drives I see in the field are bad. So we go out to a place where supposedly the drive is good. It's known to be good because people are using it and there's data on it that we want. And we go to image the drive and there's a problem with the drive. 25% of the time. That's a pretty large number to go out into the field and try to do 20 drives and have 5 or 6 of them that are going to be bad while you're out in the field. Just a couple of weeks ago, this is a picture from a job that I did probably 30 days ago. And so I took these. This is a VOOM hard copy. This is a VOOM hard copy 3. And I had some hard drives that when we hook it up, when it was imaging, this is what it would say. It would just say, task failed, cannot recover. And then the device would die. All you can do at this point, no matter how far along it is in the process, is either quit and stop or go use another tool or do something else in the hopes that you're going to make it. Otherwise, in a lot of cases, you can't take the drive with you. Sometimes on these jobs, these are live systems, and you're an investigator coming in to get a copy. Even if it's for the federal government, you got to take the copy with you. You're not taking the original. So I can't take their drive and leave. They're also going to blame me. They will blame me and say, well, the reason that the drive went bad was because you were messing with it and it's your fault. So that's the other problem is, at least if you can recover it, then you can kind of nullify that whole thing. Now we're only talking about hardware. We're not talking about the loss of data. which is much more critical. So these devices will just fail physically in the field. So this was a small drive, a 20 gig drive that I was doing, and it fails at 11, and that's it. Like after that, you get nothing. So you don't get half of the drive, and this happens all the time in bigger drives as well. So you move to another device. This one is the Falcon with its pretty Star Trek interface. And basically, this is what they do. They'll sit here and they'll count read errors, but eventually it'll just die right in the process. You'll just see it, oh, bam, I'm done. And it doesn't make it any further. It'll just count the errors. And again, it's padding that area with zeros. And then this is a tool called X-Ways Forensics, which I think is probably one of the best forensics tools that there is out there. Anybody using Ncase and FTK, you should really just stop and go get X-Ways and take a look at X-Ways. Will just pound Ncase and FTK altogether. But in this particular instance, it's trying to image the drive, and of course we still have a problem. It can't do it in software either. I have a better chance of doing it with X-Ways because X-Ways has 3 or 4 different kinds of ways I can read drives. I just didn't go through all of them and may have eventually been able to get it, but it would have taken a lot of time. So here's where I'm starting to say at least what every imager should do, regardless of whether or not it's forensics or data recovery. So this is a critical one. Should you not be able to power off the drive, power the drive back on, and continue where you left off? So if you have a bad sector and it's a problem, why not just turn it off, move a couple of sectors to the right, and then start it again? That seems like a very logical thing, that you should not have to start all over again. Every single forensics imager out there pretty much has to start all over again from ground zero. If you fail, it never continues, can't go forward from there. There's a little granularity in Ncase where it can do a couple of things with this imager, but otherwise, everybody else you have to start all over again. Non-contiguous imaging. If you are imaging a hard drive, you have to image it from the beginning to the end of the hard drive with any of those other tools, all of those tools that are out there. None of them think of it as non-contiguous. The sectors are what matters. It doesn't matter if the whole drive was done in one fell swoop. If you can do chunks of the drive at different times and put them in the right place, they're numbered, they're in order, so all you have to do is fill them in, then it would be very easy to fix this problem. And that kind of goes with the other one that's called reverse imaging, because let's say you know that 11 gigs has a problem at on that 20 gig drive. So I could read it from the other end. Why can't I start at the beginning till I have a problem, then go to the end and go backwards till I meet the problem that I had? So data recovery imagers do that every day. None of the forensics tools do that. Not one of them. Not a single one of them does any of the things in this list. And they are powered devices. They have their own control. There's absolutely no reason why they couldn't do that, except for the fact that no one wanted to change the code. Everybody's using some dumb DD engine, and they're not doing any advanced things at all to try to do that.
You mentioned that data recovery does things differently than forensics. What differentiates something as a forensic tool versus a data recovery tool?
I'll show you in just a second. We're almost there. Okay. So in this list, there's a couple other things, and I'll explain these as we get to it. One of these important things that people don't seem to clearly understand is passwords. You know, physically on your laptop, when you power up your laptop and you go into the BIOS or you go into EFI, you have an option for adding a password to your hard drive, the physical password to the hard drive, right? You guys know what I'm talking about? So that when you start up your computer, it won't go anywhere at all if you do not enter that password. And that's really technically a hardware problem from a standpoint of forensics dealing with it, because it's stored on the platter. There's a special area on the platter where that data is stored, and that data is also stored in clear text, by the way. So the data, your password, is stored in clear text on the hard drive. It's just not accessible to you. It's in a special location in the system area that's specifically known by this laptop or by your device or your tool. The thing is, though, when that setting is on, there is a command that's, every time your drive identifies itself, there's a set of commands that says, I can do these things. So there's a list of these commands, and they're called disk passport. And it's really passport, just like you have a passport, and it has your information, your social security number, whatever else on it. From that standpoint, that's exactly what this tool does as well. And they can tell you that there's a password that's set on the drive. No forensics tool does this. What they do instead is they just have error after error after error. They cannot read any sectors from the drive. So all they do is error out on every single sector. But they never report, you have a password on this drive, which would be a simple thing for them to tell you, even if you couldn't do anything about it. It'd be a simple thing for them to tell you, there's nothing wrong with the drive, there's something wrong with you having a password on this device. None of those tools, again, do this. So this is a tool that's called Atola. I know it's a little hard to read. The thing that I care about over here is the part that's a little bit clearer, which is that same hard drive that we could not read earlier. I threw it on this device, and I was able to read all the sectors. Now, we know that there was at least 21 errors on that drive. Now, this one picks up 55 because it made it further than the other devices did. And so this is reading in a particular way. If any of the other forensics tools could have read this, it would have 55 sectors padded with 0. This tool actually read all 55 sectors and recovered the data from those 55 sectors. So physically did the job and wrote that to its correct location, rather than ignore it, skip it, or just fail altogether. And this is common. This is like a daily event that I have in dealing with drives that come in from forensics that people can't read out there in the field. And I'm fine with that because I make a lot of money because they can't read their drives, and I can read their drives with some special equipment or some special tools. So, and I'll show this more in a minute, but this tool is called an Atola disk imager, and this one's an Atola forensics disk imager. One of the other tools that I'm using is called a Deepspar disk imager, and there is another more advanced tool that's called a PC3000. It's a stupid name, but that's what they called it. So, so when I'm testifying in court, now this is one of the biggest things. So the police put a guy on the stand, and he says, yes, I imaged this drive, and I did really well, but I missed, 24 sectors. So I missed a chunk of data. The drive wrote 0 anyway, so I have 0, but that's okay. It's a small amount of data. So he's sitting on the stand, and he says that. Now I go and I sit on the stand, and I say, well, there were 24 problems, but I read all of them, and I actually know what data is there. So he has no idea what is there. So inherently, the jury or someone else is going to believe I am better than he is. So we've just completely invalidated most of what the police might have said or what the opposing, because I could be on the side of the prosecution as well. So, but in 12K, there's plenty of space to create doubt as well. What was in that 12K? Could it have been a spreadsheet that said Bob's passwords and it was really Bob that did this crime? So that's really the question, is that enough to create doubt? Because a jury doesn't have any idea how big 12K is. You guys might know that 12K is not very large, but it could contain IP addresses, for the example, which it doesn't need much space to store some of this content. It only needs 4 bytes. So you have a lot of space that you could actually do stuff. So in my mind, they really need to be more thorough, because I can pretty much trump whatever they're doing just by recovering that data. So here's an example of where a lot of people will, and I'm sure some of you have seen this, if you've done a physical recovery yourself before, you got a crash drive, you go in and download some software, you recover some stuff, and then you go to look at it on the drive and some of the data is corrupt. And this is what you get sometimes for some of the pictures, because you could have had just a couple of sectors that were bad right here, but now it throws the algorithm off. You could actually have the rest of the picture, but you're missing a couple of sectors, so it throws the algorithm off and you see trash. And I've been in cases before where they show me the top half of a kid's head or something like that, and then they assume what's going on below it. I've literally been in that case where they assume what the rest of the picture is. And this is an example because, a lot of people will say Batman's standing at, Gotham City and he's on the square or he's on some steps or something. They'll say that this guy over here has probably got a guitar or something. Like they'll say a whole bunch of things. So if I could recover the data and I could do it in a specialized way where I've recovered the rest of that 512 bytes instead of padding it with 0, then I might actually get a result that looks more like this. So it is possible that you can come up with the wrong conclusion based on these half pictures and these half things, which is why they normally don't let evidence into the courtroom that's not complete. If it's not complete, or it's not a full copy, or it's not a full image, then they normally won't allow it because it becomes kind of like hearsay. You don't know what the rest of the content is. But I've seen them do it, and more, it's becoming more and more common they're getting it in. They're actually able to say that half a picture was good enough, and that they're getting it accepted because people think that, they've watched NCIS enough or something and they know how this works. So that's...
CSX cyber.
What?
CSX CSI cyber.
Yep, all the cybercrime stuff, and he runs into a room, and 3 minutes later he comes out and he can tell you everything. Like, no, that's not how that works.
All the virus code shows up red.
With the right words highlighted, or they zoom in on your license. Anyway, so there's a whole list of reasons. I already gave you why they're using these tools, and they're continuing to do this, but they have no incentive whatsoever. They're hiding all this content. So they're continuing to use things like this. So DD would be a normal one they're using. This is a more advanced tool than DD. It's open source, again, still. It's another Linux derivative. It was written by the Department of the DoD, Department of Forensics Lab. And it has some abilities to at least deal with a minor amount of some of the errors. It's still not extremely thorough, but this just shows that there's other tools out there that actually have some advanced features, but only one of the forensics imagers that I looked at used a more advanced version, used this version, which was the Ditto. The Ditto was the only tool that used this out of all the forensics imagers. It's CRU Labs is the one that makes that. So there is some advanced features. There's another open source tool that's out there that's actually very advanced. It's a Linux derivative. That's DD Rescue. DD Rescue is a very common one that a lot of people in data recovery who are trying to do things with just software and no hardware capabilities. The things you're missing without the hardware, though, are things like, let's turn the power off and turn it back on. Let's keep track of where the sector was that we just read and then continue on from there and do hard resets and things like that, which DD Rescue can't do by itself. You could probably trick it, or you could probably do some things with your machine to make that happen, but that's the closest thing from a standpoint of the possibilities. Not a single forensics imager that I found used this one at all. This has been around for a long time, too. This has been around for a decade, and not a single one of them used the more advanced features. They used straight up raw DD to actually do their imaging processes, if that tells you anything. So at least from this standpoint, the vendors don't think that this is a broken problem, primarily because in the old days, the whole issue came up with imaging was that the drives were supposed to be good to begin with. Now, I'm actually seeing a huge amount of them with problems. They just don't want to spend the money. Why would they spend the money on an engine that you can't see when they can make a pretty interface that looks like Star Trek? That's really important to them. So if it's really pretty and looks like it does a lot of good things, unless somebody's testing it against damaged drives, they don't know this. And when I've talked to the vendors about the things, they don't even understand what I'm talking about. They actually have no idea. Even the techs have no idea. So here's an example. This is a tool called the Deepspar, and this is a Windows. They have a Windows view of what happened to the drive because the actual device runs in DOS, and it does quite a bit. It's a physical piece of hardware. It is a piece of hardware, but it runs in DOS and can control the device and do a lot of things that you can't do otherwise at all because there's no drivers. It's physically doing it in DOS because it can talk directly to the hardware. So all of those dark green spots right here, those were all errors. Those were all ones that had timeouts and errors. Windows couldn't see them. Windows only reads a sector up to 600 milliseconds. If it has a problem after 600 milliseconds, it just fails and will say CRC or whatever and just fail and not open the file. Well, sometimes all you have to do is increase the amount of time that you're going to take to read something. And that would be indicated by these green ones where you're actually doing something that would be a problem. Then you've turned around and read it. You've increased the time, but you've also done something called ignore ECC. Every drive, every time that there's a sector that has an error, the drive is going to return 0. But you can actually tell it in certain instances, I would like that data anyway, no matter what it was. And then you can build your own array or try to build your own software around it to say, what was the good guess? What was the data? I got this data 99 times. Which ones were the same? And you can actually parse that out and do something with it. So there's no way any forensics tool would have made it through a drive like this. So anyway, I'm trying to get away from zeros, but I'm going to show you, in reality, this is what a sector looks like. A sector, everybody's been told, and maybe people know in here or don't, but a sector is normally 512 bytes. So every single sector has a huge amount of tracking data. All of this other stuff is all the tracking information that's actually sitting there at a sector. There's your sector right there, your 512 bytes. So every time you try to read this, there are specific types of errors. So as an example, there's an address error, and it'll actually give you ID not found. There's another one where it cannot read ECC, and it has to skip and quit, and that would be its UNC and this is ECC, where the ECC actually fails, and then there's another one called address marker. There's a whole slew of these. There's a whole pile of these types of issues with regards to content that's around the 512 bytes. Every single data recovery tool that is hardware-based, at least, all reports every one of those errors. It'll tell you exactly what was wrong with the sector and where this problem occurred. Guess how many forensics tools do? 0. That's correct. They don't report. They have no idea why there was an error. Absolutely zero. The drive told them why it was an error. They just ignored it and threw it away. They didn't even bother to try to figure it out. They have absolutely no idea. Not a single forensics tool does this. That would, to me, be the definition of forensics. If you're sitting there testifying about something in a court case, don't you think that you should be able to explain the detail surrounding what the problem is? Data recovery guys can, but forensics guys can't. I mean, and who has the most money here, as a matter of fact? Forensics guys have an infinite amount of money by comparison to the data recovery guys. Data recovery guys buy one tool and sit on it for 20 years because they don't want to spend any more money. So they'll do things the hard way to save a dime. The forensics guys are spending, you know, anywhere between $4,000 and $20,000 a year on every single tool that they buy. But none of their tools are advanced. None of them are doing this. There's a whole list. There's actually pages of this content, and I'm not going to keep going through all that. But we have a bigger problem today. If you had a drive that previously existed that had a 512 byte sector and something goes bad, how much data did you lose? Let's just say your 512 byte sector goes bad. You lose 512 bytes. That's all you lose, one single sector. Anybody seen these drives? Do you guys know what these drives are? They've been sold since 2010, 2009, 2010. You all probably actually have them. You probably, every drive just about today does this. And if you can't read what this says, this is called an advanced format drive. To achieve full performance in Windows XP, you must use this WD Align software in order to align a single partition, blah, blah, blah. Now, the problem is they put this label on a drive, but they didn't explain it to anybody. They didn't explain what the problem is or what occurs. What happened is they went to 4K sectors natively on the drive. So instead of doing 512 bytes, they didn't want to keep tracking that, and they will do, manufacturers will do horrible things to the drives to make it sound really good from a marketing perspective that will do horrible things for you, but it sounds really awesome when they tell you, oh yeah, 4K drives are faster, we can read this data, we can do a whole bunch of things that we didn't do before. The problem here is partition alignment, because until Windows Vista, we did not have the ability to have a partition everywhere on a disk. We had to put it on one side of one platter, always. And it was a calculation. Now, it's not reality anymore. It changed a number of years ago when we went to what's called LBA blocks. It's not in reality on the side of a platter, but the calculation is the same on that side of the platter. So there is a calculation that says, I'm going to start a partition on one side, and it had to do with speed of your drive. When you look at an old hard drive, you would have a stack of heads that would be inside of, let's say you have 4 platters and you'd have 8 heads, and that whole stack would be moving together. Why does the whole stack move together? Anybody know what's happening? Usually when I ask, what?
Magnetic resonance?
Well, why would all of these heads be moving together? How's the data being written? You have any idea? What's that?
It's in parallel and sequential.
So that's what everybody says. It hasn't been that way in 2 decades. And that's how every class and everything today tells you, including the EC Council, including a number of other ones that I have read. They all tell you that that's how the data is being read, that it's being written down through and read from a cylinder's perspective. That is absolutely not true. It is not. Yeah.
So, not doubting you at all, but if that's the case, how do things like read ahead work?
How do what? Yeah, well, that's still primarily, there's 2 ways that happens. That's native command queuing. That's what you're referring to, is things like the native command queuing, the caching process?
I don't know. That's why I'm asking.
Yeah, so there's a caching process. Most drives today have cache, and they have physical DRAM. And when the head is ahead of where you're reading, and here's the really cool thing, it's only when it's going forward. It's not when it's going backwards. It caches the content into RAM and then delivers it to you faster because it already read the data. It's not waiting for you at this point. However, and I'll prove it to you here in a second, what happened in the mid-90s IBM came up with this method of writing data to drives based on speed. Where's the fastest location on your hard drive? Outside edge. The outside edge of the disk is faster. Not because it spins faster, it doesn't spin faster. It's because the head doesn't have to move to read more data. You have more sectors physically around the outside edge of the ring than you do at the center of the ring. So therefore, if it stays there, you have no head latency. You have no issue moving your head or doing anything. So in order for you to read data, and you've all seen that picture, you've all seen the defrag picture that Norton used to throw up there, and they would actually show you, I'm moving all the sectors to the outside edge. That was in reality exactly what was happening. Things are broken up into something called zones. And what you can think of a zone is a little football field of data. It's a whole ring, a cylinder, of where the data is going to exist on the platter. I'll show you a picture here in just a second. So to finish this part, before I show you that picture, they're using 4K sectors. This is what 512 used to look like. So this is what 512 bytes looked like. And you know that whole picture I showed you that had a whole bunch of other crap in it that had to do with the sector? Well, that's all here. They're just not including it in their picture because there's some null space. You have to give the head a break when you're moving your sector from one location to another. So you're giving it a break. And that's what this thing called the sector gap is. It's just a break in the sector down here where you see these bytes of null, because the head has to have a break. It can't say high, 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 low. You have to give it a break of a chunk in the middle so that it can actually figure out there's a new sector coming. So that's what's happening here. Now, what they decided to do is they decided to whack this. If we just put it all into 4K, and we can get rid of all those null bytes in between. So everything else is the same size. Everything else has to be the same size. ECC is the same size. Everything's the same. The only thing that happened is they got rid of all those nulls, and they added about 11% of space to your disk. However, when a sector goes bad, how much data do you lose? So all those sectors, if they were reading them in forensics tools, and any one of them turned up bad, it's now times 8. Right? So it used to be 512 bytes, and that would pad it with zeros. Now it's times 8. That's a huge amount of space by the time we're done with 12 times 8. I mean, those things can continue to grow. And so this is going to be a continual, huge problem if they don't correct this in forensics. Every time they say, I got a bad sector, it's not one bad sector, it's 8 bad sectors. That's what you're looking at now at this point. And all those other tools read the content natively. So every single tool in forensics, every one of them, no matter what, even if it's a 4K drive, they read the sectors 512 at a time. So they will make that request 8 times for that sector. Whereas forensics tools have a thing that's called long sector reads. They will actually say, oh, I have a 4K drive, I only need to read that 1 time. That makes the imaging process 8 times faster.
Forensics tools or data recovery?
Data recovery tools. If they read them natively, it makes it 8 times faster. No forensics tool today that's not one of the 2 data recovery forensics tools will read them in native 8K. I don't know a single one of them that will do it. And several of them, Tableau has a huge problem with some of these, and continual upgrades and other things. So it'll be 8 times faster. So now, an Atola Imager, which I don't know if any of you know speeds or whatever else has to do with things, but normally when I said you could do between 200 and 300 gigs an hour, an Atola Imager can read up to 500 gigs an hour. It is the fastest imager I've ever seen. So if there's no problem at all, I can copy 500 gigs an hour. So I don't know of any other tool that can even come close to that from that standpoint. So this is what the Atola Insight Forensics Imager looks like. It's a little box. It has 3 target ports on the side. It has a source port over here. It can also do PATA drives. It has a built-in write protection switch. It has all the same features that you would have in any other forensics tool from that standpoint, except that it also can do imaging recovery of those sectors at the same time and a lot faster at that point. The Deepspar Disk Imager is one of the other tools. It's really a card. It goes in your system, and then you can use Windows software and DOS software to talk to this particular device. It has input for all 3, the SATA and a standard PATA, and then you can use converters for everything else. And it has a daughter card that can go with it that you can plug in, that you can do more drives at the same time. And both of these tools, both the Atola and this one, you know those passport drives that you buy today? Anybody open those little Western Digital passport drives? What is in there? What is it connected to? How can you connect that to your system? It's a what? Yeah, it's a SATA to USB. Okay, so they used to have an actual SATA connector in there, and then they'd use a little bridge board and they plug it in. But now they don't have one at all. Now it's a SATA to USB bridge connector built in on the board. And there is no SATA coming out anymore. It comes out USB. So in order to actually make it SATA again, you have to break it. You have to break 4 capacitors, you have to resolder 4 wires on, and you have to connect the SATA connector so that you can read it to do recovery. Because for those of you who don't know, USB sucks. It sucks. You cannot use it for recovery. Everybody I talk to, when they first start this process and they're thinking about being a recovery guy and they come to class, the first thing that they're doing is they're telling me these stories about, well, we took this, we put it in a USB enclosure, and we connected it to our system, and we tried to recover data, and we cut. And like, you could solve 80% of your problem right away if you just connected it to the motherboard. Just don't connect it to USB. You can solve a lot of problems connecting it straight to your motherboard because your motherboard has a controller, and you can get a better controller, by the way, than that one that will actually do better error correction, and you'd be able to recover sectors that you couldn't recover otherwise. So get rid of USB. Now, the problem with USB is USB 1 and USB 2, they both were just dumb controllers. Nothing you could do, nothing special. They literally, you just make a request. It goes through this, nickel chip that you buy from China or whatever, whoever got the lowest bid that week, and you hope for the best. Now, USB 3 is a different animal. USB 3 is a lot more like an Ethernet protocol. You can make requests. You can do certain things. The problem is no tools understand how to make the request in the forensics world. Only in the data recovery world. In the data recovery world, they can actually talk to USB 3 drives natively and treat them like standard SATA controllers. So both the Deepspar and the Atola have an input directly for raw native USB 3 drives where you can do a recovery without breaking them. So you don't have to break 4 capacitors and resolder on a SATA connector. Now that's always been an option so far, that you could break it and resolder these connectors on and then actually do a recovery anyway. But at least this stops you from having to, you can immediately plug it into the system and start working on it. But if it can't read, none of the forensics tools can read at all. Zero. Not a single one of them can do it. So these are the only tools. This one can read USB as well. This is the only American-made tool. This tool here, all the top tools in the world, none of them are made in America. The only one that's made here is the CPR tools. This tool is from Ukraine. This tool is from Ukraine. This tool is from Florida. This tool is from Russia. So these 3 that are from foreign entities, believe it or not, every government agency that you work at or been to or seen has these 3 tools, all from Russia or the Ukraine. Sometimes they think it's a security risk. Sometimes they don't. There's all kinds of problems buying them because the one in Russia only accepts Western Union transfers of money to buy it. So they can't use credit cards. We got sanctions and all kinds of things. They can't buy them anymore. But I will tell you, this is the most powerful tool in the world. This tool is the most mature. It's been around the longest. It's called a PC3000. It can do firmware. It can talk to drives and firmware. If you want to, let's say you want to travel with a hard drive and you don't want TSA to be able to copy it, you could literally go into the firmware and turn off an entire platter. Just turn it off. Just turn it off, and when you travel, they can never read it. They can never. You get to where you're going, you turn it back on. Like, that's all you got to do. Just physically turn off a platter. Turn off however many platters you want. So there's an option for you to be able to do those kind of things. Anything that you want to do, it's doable with this tool as a whole. So, and just real quick, the only, at least from a standpoint of the only tool that's in America, one of the awesome things about this is a forensics imager. It does have a minor bit of data recovery built in. It has some functions, but it's not available the way that the tool looks right now. This is the cool thing about this tool is it's very small and quick and easy to set up. You can go and plug it in, get your drives running, And then you plug in a USB connector into your laptop, and there's another piece of software that will then let you control the imaging process. So you can start the imaging process and do it all from the box. But then if there's a problem where you want to control it, you can plug in a USB adapter, plug in a USB cable into your laptop and use the software to control it, including things like skipping sectors and doing reverse. And so this is the only tool in any of those categories that's even close to what happens with these other three tools, and still be a forensics guy and still be a forensics imager. So they don't technically call it a forensics imager, but that's the way it goes. So there's a huge amount of the problems that can be solved here, but I'm going to show you some pictures rather than tell you all this crap on this list. So these tools, at least the Atola itself, does diagnostics on the drive. It actually will populate registers on a board and then read them back and try to tell you what's wrong with the drive. It'll run through a variation of a list of 5 items and then break those down to try to tell you, oh, you have one bad head. You could turn the head off and still read all the other platters on all the other areas. So no forensics tools do that. Again, you can literally say, I have, you start up a drive and it goes clunk, 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 and you can't read it. You can literally turn off one head that might be bad and read all the heads from all the other platters on the drive. So you might not get 100% of the drive, you'll get 70% of the drive or 80% of the drive. And now people are thinking, well, the data that was written down through those cylinders, well, that's a problem. Well, that's why I said if you break it up, all the stuff, all the data is written in chunks. It's called zones. And I'll show you a picture of zones in a minute. So you can read consecutive data. It'll do 2 gig chunks or 4 gig chunks or 8 gig chunks all at once on one side of a platter without changing heads to the other side of the platter. Only one head can be on or off at a time. The entire stack is just being dragged along with it. The rest of the stack is doing nothing. So if you have 8 heads in a stack, all the other heads except one are doing nothing. They're just being dragged along. So you're only reading or writing from one head at one time at any point. So this tool will run through that. These tools will also do one other thing. If you'll look here at the bottom of the screen, while you're imaging the drive, it shows you the sectors in hex as it's reading them. It reads them and writes them and shows you in hex. So you are not blind. Sometimes what happens is a head will time out and it will just go 0 to the end of the drive. That's the same thing here in the Atola tool as well. It'll show you every single sector as it's reading it in hex. So if there's an error and from here on something screws up and all you had was zeros, you would see it on the screen. You would know while you're imaging it something's wrong. And you can still go back. You don't have to do this concurrently. You can stop it and go and image any part of it at any time that you want. So you can start in a new spot and you can just jump to a particular sector and image it at any point in time. It is not concurrent. I already told you USB sucks. USB is a mess. So this is a bad head. This is what it actually looks like. This is 4 heads. So 4 heads on the drive. So there's 1 section, 2 sections, 3 sections, and there's the 4th one. This data from 0 to 4096. So this is a chunk of data that's done on 3 different heads that can be read, turning off 1 head. It's all consecutive from that standpoint. It is not written down through all the platters. So you can actually see that. There's actually an item in the list. It's called zone tables. A zone table breaks this content down. I've got a picture of a zone table coming up. In this list, this is a list of things that are written to your platters. Most people think the board contains a lot of intelligence about how your drive is going to work and that swapping boards will do a lot of tricks. Your board at most contains 4 possible tables. The rest of it is all written on the platters. Your serial number, your model number, those things are written on the platters. The platters has its own complete operating system that the drive needs to function when it first starts up. So this is just a small list of those things. The bad block tables, there's actually 2 of them. There's more than 2 of them, actually. And then, as I told you before, there's a lot of timing issues. This is what one of the controller screens for the Deepspar looks like. And if you look at the details, I mean, it can literally break out every single thing. There's a huge thing here also that most people won't understand, but it's called LBA 28-bit to 48-bit mode. It's an obsolete command that almost every drive still allows on any sector below 137 gigs where you can read it more accurately if it has an error. But you have to put it into LBA 28-bit mode. We upgraded in 2002 or so to LBA 48-bit mode, and they got rid of this command. So a lot of times we can go back and force this command and at least read the first 137 gigs of the disk better than we can read any of the other stuff. But there's a lot of little details like this. You never see these in forensics imagers. In forensics imagers, you get a little thermometer bar that goes across, and you get a button that says go, and that's it. That's what you get. Go. Thermometer bar. So these are just examples of some of the stuff you can do. You can program it to skip, come back. It can basically do all the good stuff and then come back and do the bad stuff later. So you can skip content and come back to it later. And my entire point here is, if your wallet caught on fire and you had $512 in it, and in your wallet you were able to recover $511, wouldn't you keep that? Or would you throw it away? You say, oh no, it was in a wallet that was burnt, I'm just going to throw it away. So that's effectively what's happening in forensics. They're throwing the content away and getting rid of it. And personally, I would keep it. So these are some of the situations where 48-bit and 28-bit help. You can also image in reverse, as I've already described. And then physically, this particular tool, and it might not make much sense to people to see it here on the screen, metadata inside your drive, which when I say metadata, I mean NTFS has a table and it's called MFT. And that's the master file table. It literally is the tree that you're looking at. The tree that you see in Windows is part of a structure in the MFT. It's a very small amount of data comparatively, so it might be about 300 megs or so. All it does is tell you the layout of where the data is on the drive. Well, these tools, all of these tools, all the forensics tools don't do this at all, not a single one of them. But all of the data recovery tools do this. You copy the metadata, that 300 meg file, and it builds the tree for you. We don't have any data. All we have is the tree. We check the box that we want, and we say, image the selected area, and it will actually image just the section of the drive that's specific to that file, and it does it in order. So it does it logically from the beginning of the block to the end of the blocks in their clusters in order without touching anything else in the drive. So the whole premise is don't touch any sectors on the drive unless you're cloning them. If you're cloning them to a second drive, then you're protecting them. You should only ever have to touch them once. You should never touch them twice. When you normally build a tree in data recovery software, the software you would just download off the internet that builds a tree, it scans your whole drive, builds a tree, then you select what you want and you recover it. You touched every sector twice, at least twice, without copying it before you've exported the data. That's a terrible thing to do, horrible thing to do. That would be bad news. So fundamentally, that was kind of the whole impression that I'm trying to give everybody as far as the list of items. I do have a picture of the zone table. Apparently, it's not in those particular slides, but I'm about to run out of time in about 1 second. But let me show you a zone table just because it was a question. There's a whole bunch of things with drives. Like you can break chips off, do things, and your drive will still run. There's things that you can do. So I'm flying through some slides. This is a zone table. This tells you which head is broken down. Now, this is right off of a drive. I saved this straight out of a drive. So if you look, head 0, there's 3 locations for head 0 here at the beginning of the drive. These are the locations, and then your LBAs. So you have a start location at 0, end is 4. But you'll look, for this zone, 1, 2, and 3, they're in order. So right here, they're the first blocks of the drive. Those are the first LBAs. That's 6 gigs of data that's concurrent and consecutive on the drive before it moves the head to another drive, to another platter. So that physically will keep your data. And when you have a platter that's scratched, you only have one of those that's going to be damaged. The rest of the data may still be fine. And it's completely possible that in your drive, that amount of data for the amount that we've just copied is all of the My Documents folder, unless it's somebody who has pirated movies or whatever. But at least from that standpoint, the data will be there. So, and this is what I was trying to point out with the cylinders. Basically, all this data, only one side of the platter, the data is concurrent. You can actually deal with 6 and 8 and 10 gig chunks, depending upon the breakdown of the table. So it's going to be on one side of one platter for those zones. All right, that's it. That's what I got. Yes, sir.
So the last drive I bought was an 8 terabyte drive, and it requires special drivers on enterprise equipment. I think it's HGST or shingling or something.
Yep.
Does that mean pretty much what you said before, we're going to have an even bigger problem with coverage?
Yeah, so what shingle technology did was, think of it like Blu-ray. You know how Blu-ray basically uses a more intense beam to read down further into the disc and you have layers, multiple layers? That's essentially what they've done with shingled, is basically they've stacked the sectors in a way that then they will read them according to their strength. And they're pretty volatile, in my opinion. I see a lot of crash drives. I see a lot of them that are terrible. And this is one of the reasons why they're also probably focusing only on the, or at least currently, on the enterprise market, is because somebody gets pissed off. It's probably a client who has a lot of money and they already are throwing backups and they're already having a bunch of things going on, rather than the home user who's going to have a disaster. But since 2006, we've at least changed the technology. Prior to 2006, the technology was almost exactly the same for 50 years from a standpoint of how we wrote data. Since 2006, we went to perpendicular encoding. Now we've got shingled, and then we've got a new type of technology that's coming out that's called HAMR, which is heat-assisted magnetic recording. So that has a little tiny laser beam in front of your head that actually heats up the platter, because if it's hot, it actually can change its phase quicker and easier, so you can have a smaller amount of space. The problem is it zaps the lubrication, and the lubrication evaporates. So they have this little container of lubrication that they say for the lifetime of your drive that they will automatically periodically spray your platter and re-lubricate your platter. I'm not kidding. This is not a joke. That you have a lifetime container of lubrication.
You gotta lube your platter.
Yep, you gotta lube your platter, and it does it on a particular schedule. So, but yes, those. And that's why those are in those higher ends. But I personally would say I wouldn't be using any of those in a you obviously are probably using them in RAID arrays and things like that, but just understand RAID 6, I hope at least, not RAID 5. Well, that's better at least from a standpoint of having duplicates, but still, just keep in mind when those things go, they go fast, and a lot of them go. A lot of times they'll have the same bugs and the same things will happen all in order. Don't use solid state drives for a RAID array. I know people think that's a really cool thing and it's really fast and whatever else happens, but trust me when I tell you, they have the exact same lifespan. So every time one of those drives dies, another one's about to go because they have the exact same sector lifespan. So RAID is supposed to be so that you have one that survives during the process of another one being rebuilt. Well, that doesn't happen if they are all going to die in the same time. And the other thing that happens is they all have the same bugs, so whatever bug kicks off one of them kicks off all of them. So all of them will die in the same breath. So don't use them, I'm just telling you. All right. Yes, sir.
So you said earlier that you get the pass run drive that prevents it from being read.
Yes, sir.
And just reads all zeros. Well, why wouldn't
It doesn't read zero. Now, see, this is the weird thing. It actually gives abort commands, so it actually will give an error every time. So your forensic software wouldn't even write zeros. It would say abort for every single one, and it would just die. It wouldn't do it. But go ahead. What's the rest of your question?
So yeah, I was gonna say, why doesn't it just read a hash 1 and 0 through the drive?
Well, you're not supposed to read any sector at all. It's actually supposed to give you an error for every single one, but there's a setting that actually says we have a password set. And my argument is they should flash every one of the data recovery tools does it. They flash a box that says your password is set. None of the forensics tools do. So, anybody else? Good. Awesome. All right. You guys can always find me and ask me questions. So, or I had teach a class as well. So.
Thank you, Scotty.